Okay, so in this video, we will consider the following fact. We will first understand why it is very intuitive, and then we will ask, why do we care about this result? And the reason is that it will be useful in future results. So here's the result. So the series of an from 1 to infinity converges if and only if the series of an from m to infinity converges for any positive integer m. And the idea here is when you look at convergence, look at what is different between this series and this series. Well, in this series we have dropped the first few terms of the sum. Imagine that m was, say, 5. Then what we're missing if we begin summing at 5 instead of 1 is we're missing, well, a1 plus a2 plus a3 plus a4. But for any given m, we will only be missing a finite sum of finite numbers, and that is always finite. So it will not affect the convergence or divergence of the given series if we ignore the first few terms of the series. And the reason why this is useful is we will see later on some results that will say, as long as the sequence, the terms you are summing, at some point have a given property, then you can apply the given result. That's why we can or care about the idea of dropping the first few terms of the series and not affecting convergence. Of course, if the series does converge, you can't drop the first few terms if you try to evaluate the exact value of the series, as the first few terms are important in obtaining the exact value of a converging series. But if you only try and determine whether the series converges or diverges, dropping the first few terms do not matter. So here's the intuition, which at the same time is a proof, but it's so straightforward that it really is just intuition. So let's expand out the series. We're trying to sum an from 1 to infinity, so we have a1 plus a2 plus a3 plus dot 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 plus, again this is an infinite series, but I'll look at some of the middle terms, a m minus 1 plus am plus am plus 1 plus am plus 2 and so forth. So if you look here, well, this is nothing but a real number, right? Each term of our sequence is some real number. If you have a finite sum, as m is a fixed positive integer, this is a finite sum of real numbers. The result is nothing but some real number. If you look at this part, well, now we have an infinite series. We are summing a n as n begins at m and goes all the way up to positive infinity. And so you see, by breaking down the original series as to the sum of the first m minus 1 terms plus the remaining of the series, what we have is that the original series is some real number plus this other series. And now we can clearly see that the result is valid. This series is a real number plus another series. So let's see. If this series converges, this series must converge as well, as this series, if it does converge, is a real number. So you could subtract this real number from both sides, and you would have a real number minus a real number is of course a real number. Well, if the infinite series here is a real number, it of course converges. And you can go the opposite direction. If this series converges, this is a real number, but a real number plus a real number is nothing but a real number. So if this series is a real number, it also converges. And that's it. So always think of it in this very intuitive fashion. When you're trying to determine if an infinite sum of real numbers converges or diverges, you can always, and I really mean here, just figuring out if you have convergence or divergence, not trying to find the exact value of the series. But when you try and figuring out whether you have convergence or divergence, you can always ignore the first few terms of the series, as a finite sum of finite numbers is a real number, so this will never affect convergence. And again, the reason why this is important is later on we will see results where it won't matter if the first few terms of the series do not have the desired property, as long as at some point on the terms have the property, the result will be applicable. And that's it.